Good morning. This is T. Shivapriya, Assistant Professor, Department of Physics from St.Josephs College of Arts and Science for Women, Hosur. Today we are going to discuss about least disk method of determining the thermal conductivity of a bad conductor. What is heat transfer? Heat transfer is a movement of heat due to the temperature difference between a system and its surroundings. Due to the second law of thermodynamics, the energy always transfers from higher temperature to lower temperature. There are three types of heat transfer. They are conduction, convection, and radiation. The given figure shows the three types of heat transfer, that is conduction, convection, and then radiation. Then we discuss about conduction. Conduction is a heat transfer directly between the neighboring atoms or molecules. Conduction of heat takes place in solids, liquids, and gases. Conduction is a common process in everyday life. For example, when one end of a metal rod is heated, the other end soon becomes warm because heat is conducted through the rod. Then holding an ice cube immediately makes your hands feel cold. Then the iron cloth transfers heat from the iron to the fabric. These are the common example in our day-to-day life. Convection. Convection is a heat transfer via the movement of a fluid such as air or water. Heating water on a stove is a good example. Then another example is the movement of air around a campfire. Meanwhile, the partial vacuum left by this movement draws in cool outside air that fills the fire with fresh oxygen. Then move on to radiation. Radiation is the emission of electromagnetic radiation. While it occurs through a medium, it does not require one. For example, it's a warm outside on a sunny day because solar radiation crosses space and heats the atmosphere. Then the burner element of a stove also emits radiation. Most real life processes involve multiple forms of heat transfer. Conductivity is a property that describes a material's ability to conduct heat. Thermal conductivity is a key parameter in measuring conductive heat transfer. It is often denoted as K and the SI unit is watts per meter Kelvin. The given figure shows that the thermal energy given to any conducting material, so the heat transfers from one side to the another. So there are two types of temperature maintained on each side, that is T1 and T2. Here the temperature difference is delta T equal to T1 minus T2. Coefficient of thermal conductivity. Consider a slab of material of length x and the area of cross section A. The opposite faces of the slab are maintained at different temperatures, that is θ1 and θ2, where θ1 is always greater than θ2. The quantity of heat Q conducted from one face to another is directly proportional to the area of cross section capital A, directly proportional to the difference of temperature between the ends θ1 minus θ2, directly proportional to the time of conduction T, and finally inversely proportional to the length x. So the quantity of heat is given by Q is directly proportional to A into θ1 minus θ2 into T and inversely proportional to the x, that is length. Here we want to remove the proportionality symbol, so we introduce some constant. Here the constant is K and it is called the coefficient of thermal conductivity of the material of the slab. The thermal conductivity of a bad conductor is determined by least disk method. The given figure shows that the least disk apparatus. The apparatus consists of a circular metal disc D suspended by 3 strings from a stand. Over this rests of a hollow cylindrical chamber S of the same diameter. It is provided with an inlet and outlet by which steam is allowed to circulate. The specimen is taken in the form of a thin disc C of the same diameter as D and S. It is placed between D and S. Here there are holes in S and D into which thermometers T1 and T2 can be introduced. The least disk experiment determines an approximate value for the thermal conductivity K of a per conductor like glass, cardboard, etc. The procedure is to place a disc made of the per conductor, radius R and the thickness X between a steam chamber and the two conductivity metal discs and allow the setup to come to equilibrium. The upper disk temperature T2 and the lower disk temperature θ1 are recorded. Now the bad conductor is now removed and the steam chamber is placed directly on the disc. The disc D is heated to a temperature of about 5 degrees greater than θ2. Now the steam chamber is removed and the disc D is allowed to cool. Now the temperature D is noted at intervals of a half minute until the temperature of the disc falls to about 5 degrees below θ2. The mass of the lower disc D is found and its thickness L is also found. Here C is the specific heat capacity. The rate of heat loss is given by H equal to mc into dt by d small t, where m is the mass of the brass disc, then c is the specific heat capacity of brass. At steady state, heat conducted through the bad conductor per second will be equal to the heat radiated per second from the exposed portion of the metal disc. So, Ka into T2 minus T1 divided by X equal to mc into dt by dt. Therefore, heat loss equal to heat gain. To rearrange the above equation, we can easily find out the value of K, that is the thermal conductivity of a bad conductor. Thank you for watching this video.